It's a kind of conspiratorial description of nature. What are the symbols in these equations representing? We can predict some quantity to 10 decimal places, and we still don't know what the theory we're using is actually telling us about the world. So I think all the evidence points towards the quantum state is not something that actually exists and moves about in the world. For the vast majority of quantum phenomena, at the very basic level, like interference and teleportation, you can explain those phenomena, but only if you take the point of view that the quantum state is knowledge. If you believe that the quantum state is ontic and really physical, then it causes problems.
Quantum mechanics is our most accurate map of reality, but if we take the map, the quantum wave function, seriously, it points to a multiverse in which everything physically plays out.
Do you think your world is behind one of these doors?
Maybe we're in some kind of liminal space.
Superposition.
Exactly.
Now, quantum physicists like Dr. David Schmid and Dr. Lídia del Rio represent a growing group in physics that says that we shouldn't take the wave function as something that really exists.
I think the sort of evidence that the wave function really is just knowledge, it wasn't really there until the last 15, 20 years, and we've really gathered all that evidence more recently. So that's why I think these approaches are taking off.
There's some approaches where you can keep hidden variables, but the price you pay is a price in like complexity, like the information that needs to be packed in every particle includes like
the entire universe.
The entire universe. Yes.
The benefit of not taking the wave function as something real, something ontic, is that you don't have to assume a theoretically heavy multiverse. And now, a lot of quantum phenomena can be explained more simply.
So the bulk of quantum theory, in some sense, has become much simpler to understand. But the ones that remain, the ones that we don't yet have classical models for, are, I think, to me, weirder than ever. Like, those, they scare me.
They scare you? Okay, let's talk about sort of one of the scary ones. Welcome to the Essentia Foundation's YouTube channel, and in this video we will discuss why some quantum phenomena are actually not that weird. After my conversation with these two brilliant physicists, I think of them as quantum debunkers. In a sense, they explain that some quantum phenomena can be made classical and are not so weird. But on the other hand, the phenomena that remain, they make a bit more weird by formalizing the weirdness. We will get to that in this video, but you can also watch a previous conversation I had with Dr. Lídia del Rio, in which she explained to me a sort of formalization of the weirdness, which is called the Frauinger-Renner thought experiment. Good to know is that in this conversation, Dr. del Rio joined in as the Essentia Foundation's research fellow to assist me and help me better understand the ideas of Dr. David Schmid, on which we mainly focus in this episode. Now, without further ado, here is my full conversation with these two brilliant quantum debunkers. When did it dawn on you that quantum is weird? Or wasn't it weird for you?
Well, I don't think it dawned on me in any particular moment. I think it was really a slow burn. And I think part of the reason for this is that I'm very skeptical by nature. And when people start teaching you quantum physics, they're like, look how weird this theory is. From the first class you ever take, the professors are warning you, don't worry, you're not going to understand this. It's confusing. I don't understand it either. And it kind of makes you a little suspicious. Like, they're not really telling you why it's confusing, and the specific things they point to and say, this is the part that is difficult to explain. This is the bizarreness. It doesn't obviously feel like it has to be bizarre. So like the uncertainty principle, people will say, you have some quantum state which you can't have knowledge about both the position and momentum of. And they say, therefore, the particle doesn't have a position and a momentum. Isn't that weird? And it's like, well, the quantum state isn't itself the particle. And the statistics, it's true that the measurements you do and the outcomes that you see will have some uncertainty. The position and momentum measurements will never both give you definite outcomes at the same time. But that doesn't imply that any specific particle doesn't have a position and a momentum. Yeah, so often people will present this as sort of the uncertainty principle shows you that a particle doesn't have position and momentum at the same time. But it doesn't logically follow from the uncertainty principle. And I think there's kind of some awareness of this, but when you first learn quantum theory, there's a lot of like hemming and hawing about can you really conclude these things or not? And so I was always just waiting, like, that isn't enough proof that it's weird, so maybe we'll find a simple explanation. And I was kind of holding out hope for that. And I think as a consequence, it kind of took me a long time to really find the parts of quantum theory that I was really convinced, okay, I can see why there's no hope of explaining this in a simple way, or at least in order to do so, we're going to have to go very far. We're going to have to really change our view of the world. And so the basic things like entanglement and uncertainty principle, I was always waiting and hoping that maybe this isn't so weird if we just think about it in the right way.
And did it become less weird, or do you think now it is less weird once you have a better understanding of it?
Yeah, I think as a kind of percentage of the phenomena in quantum theory, most of them now I don't think of as very weird. So the bulk of quantum theory, in some sense, has become much simpler to understand. I think not just for me, but for the people in my expertise who are studying kind of what kinds of classical models can we make of these phenomena. I think we now have this huge range of supposedly weird quantum phenomena that actually we have pretty natural explanations for. But the ones that remain, the ones that we don't yet have classical models for, are, I think, to me, weirder than ever. Like those, they scare me.
They scare you. Okay, let's talk about sort of one of the scary ones. So what's a scary, weird quantum phenomena?
Well, the quintessential weird phenomena, and the one that brought a lot of us here to Vienna, is, of course, Bell non-locality. So kinds of correlations that you can witness between distant observers that are stronger than you can explain in any sort of classical common cause way. So that the standard way to generate a correlation is you prepare it in advance, or you send a signal. And if the people are far enough apart in the experiment, then there's no potential for a causal influence. So no signal could be sent from one to the other. So the only remaining possibility, you would think, is that there's some properties of the system that are prepared in advance, and then the local measurements in this experiment are going to reveal something about those properties, and any observed correlations come from the detailed properties prepared in advance of this common cause. And what Bell showed basically was that common cause can't be interpreted in the standard way as just a classical hidden variable, something with a set of properties where the measurements just reveal those properties.
Yeah.
And I think even to date, this is essentially the most striking illustration. Although by now there's actually some other phenomena in quantum theory that are giving it a run for its money in terms of the disturbance.
Before we get into those, what we haven't discussed yet, Lídia, because we had Sandu Popescu explaining to us sort of the very well explaining non-locality, and with Matt we talked about sort of the different interpretations on the table. But how do you, and both of you, but maybe first you, Lídia, how do you account for non-locality? Is it the quantum field that there's a oneness underneath what we think are two particles sort of distantly, and that accounts for it? How do you account for non-locality, or doesn't it disturb you? In that sense,
it does not disturb. I mean, it's just like this common cause. Yeah, there's a common cause, but it's not a classical common cause. It's the state. It's entangled. It has a special property. There is not the kind of properties that you can write down in a notebook, or like a strategy that can prepare in advance. For me, it is what it is, and we need to accept nature as it comes.
Yeah,
I don't feel the need to find. I don't know. Do you feel the need to find an interpretation, a hidden variable for this, or?
Not a hidden variable, but I do feel the need for a deeper causal explanation.
Yeah.
And the direction of the explanation that I'm looking for is similar to what you described, that I think I agree that we can't interpret this common cause as the traditional kind of hidden variable, where we typically think of the hidden variable as just a list of the possible properties of the system. And that's such a broad statement, right? It's hard to imagine what could be more fundamental. Like what other notion of ontology could you have other than a set of properties? You'd think you just collect together whatever properties, position, mass, spin, color, charge, take them all together and just call that this common cause. And yet it's not something that can be described for any sort of collection of such properties. So I agree, and I think then we have to look for some new notion of an ontic state, an underlying kind of variable or common cause, some new kind of mathematical description, a new kind of object that can act as a common cause. But we don't really have any clear proposals for what that common cause would be that aren't sort of merely descriptive. So I think you could just say, what Lydia, I think, was saying, that it's just a common cause. It's
it's the quantum state, right? So we have, on the one hand, we have like, oh yeah, it's this list of possible answers to the questions you'll ask, right? The really classical thing.
Yeah.
And we know it can't be this, right? Bell's theorem rules out. Then we'd say, oh, on the other hand of the spectrum, we have the common cause is the quantum state, and we need to take, our variables need to be quantum variables, and instead of talking about like classical events and so on and causal, we need to take the quantum state. And like the question is there something in between? Is there something a bit more deeper that gives us a little bit more understanding?
Yeah. And that one for me still, I get the sort of, for people, the hidden variables is of course what we usually think of, what Einstein was in search for. Just think that there must have been some form of communication or information all along that sort of accounts for this. Now that's ruled out. You guys agree on that, right? The physics community. Are people still in search of local hidden variables?
There's like this Busstra thing, So there's some approaches where you can keep hidden variables, but the price you pay is a price in like complexity, like the information that needs to be packed in every particle includes like
the entire universe.
So it's not a very simple theory, right? So
and moreover, it's essentially a variant of many worlds. So you also have this many universes.
Yeah.
So it's like whenever you want to drop one of these intuitive things, you end up with something.
Yeah. but when you say the other explanation is the quantum state, what are we saying then?
Yeah, this is like, you can't go deeper than this, right? It's just a quantum state and that's it. You're not going to find a deeper explanation.
It's a very operational kind of coarse-grained description. I would say it's more descriptive than explanatory. So like the quantum formalism is this beautiful prescription for describing any sort of experiment you want, and it gives you perfectly precise results, predictions for the experiments you can do. But it's the challenge is taking that sort of descriptive, predictive framework and endowing it with some sort of explanatory power. Like, what are the symbols in these equations representing? Is the wave function really an object in space, or is it some kind of description of knowledge? And everybody has different answers to these questions.
Yeah.
Whereas when you go back to classical theories and you have particles moving around with positions and momenta, we kind of have an immediate tethering of those mathematical objects, x and p for position and momentum, to things in the world. But with the wave function, we all disagree on what the tethering of the mathematical object to the entity in the world should be. And depending on your tethering of these, you end up with very different kinds of pictures of the ontology and pictures of the metaphysics.
And it's predictive power. We have a black box theory about nature, right? We don't know we don't know sort of the underlying mechanisms at play. We only know that this theory gives us sort of the outcomes predicted, but it only does so, right, with large numbers, right? On large numbers. I mean, with many particles, we get a distribution, a perfect distribution with very high numbers of particles, for instance, right? If we fire them in a double slit. I mean, on single particles, is the theory also predictive?
Yeah, I mean, there are also no-go theorems and paradoxes that are more deterministic. I mean, but of course, even within this, you can still ask questions that have deterministic answers. So like if I send a photon through a polarizer, that like a grid that's like vertical, and then I ask, am I going to find it in the like vertically polarized? And the answer is going to be yes.
Okay.
100% of the times if you do the experiment carefully enough, right?
So even within quantum mechanics, there are then deterministic outcomes.
There are some deterministic things, of course, like you always have noise and everything is...
As you said, there are certain questions to which you'll have definite outcomes.
Yeah.
So if I prepare a particle being at this exact position, its momentum is totally random. But if I measure its position, well, it's going to be right here where I put it. And so that's like a definite prediction within quantum theory. But I think the spirit of your question is kind of going back to what I said about the uncertainty principle, that we know the wave function has some constraint on how localized it can be in both position and momentum. But then there's this question, does that imply that a given particle can't be localized in both position and momentum? And well, it doesn't imply that, because the wave function is not itself a particle. It's a description of a particle, and people disagree on what kind of description that is. And so we have models which try to give the particles sort of definite positions and momenta, which at a statistical ensemble level behave like the wave function.
Maybe nice to unpack for a general audience what the wave function really is. So my understanding is it's a piece of mathematics. So it's a formalism that describes the behavior of a particle in superposition. And with some mathematics you guys can perform on it, you can predict what outcome I can get when I perform a measurement, but it doesn't tell you what the particle is before you measure it. Is that the way to put it?
That's pretty fair. It's got predictive value. We use the wave function to make predictions about the particle, about what we'll see when we do measurements on the particle, but it doesn't immediately tell you specific facts about the particle. And people disagree on precisely what you can deduce from just looking at the wave function, aside from these basic predictions for measurement outcomes. We all agree what the predictions for measurement outcomes will be. That's what quantum theory tells you exactly how to compute. But whether you can deduce that sort of the particle is some mass density that's spread out in a sort of in the same way that the wave function is spread out, or whether it's actually a point particle that's moving around with definite trajectories in a way that's just sort of statistically consistent with this spread out wave function. Those are sort of very different views of what's actually going on. The sort of standard view that you'll be taught in a classroom is that when we send a single photon through two slits in the wall, for example, it behaves like a wave. We see an interference pattern on the detector, and therefore we have to think of it as a wave for the purpose of explaining those experiments. But then for other experiments, like where you put a detector in each slit and you check which slit it goes through, only one of the two detectors will ever fire. So it's as if this particle is localized and not like a wave. And often people will say, this is wave-particle duality. Sometimes it behaves like a wave, sometimes like a particle. And moreover, perhaps it seems to depend on what question you ask, whether you put the detector there or not. So people sometimes interpret this as a kind of weird observer dependence of reality. People sometimes also try to interpret this as a kind of non-locality, where they say, if the particle went through one slit, nonetheless, a phase shifter on the other slit will still affect the interference pattern. And therefore, the particle had to somehow know about the phase, even though it's in a distant location, this separate slit. And so people have tried to then say that this is evidence for non-locality. But it's not, there's no sort of rigorous no-go theorem backing that up in the same way that Bell's theorem kind of gives you a rigorous backing for non-locality. And as a consequence, then, you can hold out hope that somebody might one day come along and provide some simple classical model where, in fact, there is a particle with definite trajectories, there's no observer dependence of reality, and there's no non-locality. And actually, this kind of model is totally possible. And it was actually invented maybe 15 years or so ago by Matt Leifer, who you interviewed earlier, and Rob Speckens. And we just put out a paper a year or two ago to basically present this model. So it took us 15 years to write the model down in full detail, but but not because the model is difficult. It's actually a almost trivially simple model, but just because sometimes research takes longer because you're distracted by other ideas, I suppose.
Cool. I don't know if I fully get this. So Lídia, may I ask you to try and explain it to me? But maybe also off camera. I just want to really get this. So, but what David just said.
Right.
So,
I mean, what they're saying is that they have a classical model, so like a hidden variable model, where you can reproduce this behavior of the particle going through one slit and just one slit and behaves like a particle, or through two you see the interference pattern and you see this kind of, it looks like it's signaling kind of thing, right? So it's not a genuinely quantum phenomenon. It's not that the same standing as like Bell's theorem or contextuality as we'll see before, right? For me, I always found it a bit weird how people are so hung up with this notion of particle and wave and trying to fit everything in nature inside these two boxes, because I mean, it's not particularly surprising to me that, it's something new. It should not behave as one thing or the other. But sometimes they mean it we see interference, or we see localized, but yeah, I don't know.
Yeah, that I found surprising, that I think Matt during the conference that said that one has puzzled me always, is sort of the quantum eraser or delayed choice experiment Wheeler proposed, where, correct me if I'm wrong, in a double slit setup would mean that you have both slits open, and after the particle has passed, so already it should have been sort of in a wave, have wave-like behavior. You close one slit and then sort of it knows you did that backwards in time and starts behaving like a... But this is sort of the essence of the delayed choice, right? You do something further down the line where a particle is already in a superposition or collapse, and then somehow the particle knows backwards in time. And Wheeler said stuff also that it seems as if we have to... you call it history creation, I think, sort of that the particle can create a different history upon measurement, which is to me utterly weird. That I found more weird than just double slit. But then I heard during this conference that isn't a real, not such a weird phenomenon, is it? But please help me understand this.
Yeah, no, it's a good question. In fact, that's one of the first phenomena that I was reading about when I was 14, 15, and I was reading about the delayed choice quantum eraser and things like that, and it was part of what got me into the field. Wheeler's delayed choice experiment, to describe it, we first have to think a little bit about what's called an interferometer, and it's basically just another way of describing the two-slit experiment, but it's actually a bit simpler than the two-slit experiment, and that's why it's kind of useful to illustrate this kind of phenomena. So the two-slit, the essence of the two-slit interference experiment is that you have two possible paths from which the particle, it originates at the laser source, it goes through either the left or the right slit, and then it ends up on your detection screen. So you kind of have it splits off and it comes back together. And the interferometer experiment is basically just a discrete version of this, where you have a first beam splitter that can split the path. The particle can either bounce off the beam splitter or it can go through the beam splitter. So now you have two discrete paths, and then you put some mirrors so that you can recombine the two paths into a second beam splitter where the particles meet, and then they can go through the beam splitter or reflect at the beam splitter and end up at one of two detectors. And so it's basically got the same pattern where you've got a particle originating at a source. It somehow spreads out, goes through two paths, and then comes back together. So it's the same basic geometry as the double slit, but there's only two possible paths instead of this whole spread out continuum of paths through the slits. And now once you have this interferometer, you can see the basic interference phenomena just like you do in a two-slit experiment. So, for example, if you just shine the laser through this interferometer, you can set it up so that the light always takes one of the two outputs. So there's constructive interference. The two paths, it's said to constructively interfere in one path, which means that all of the light leaves out through that path, and all of the amplitudes of the wave cancel in the other path. So this is now a perfectly set up interferometer. And then to see the interference, what you do is you put a phase shifter in one path. So this could just be like a little sliver of glass, for example. So that glass, we know that light is a wave. It's got this oscillatory behavior. And when you put a piece of glass, it sort of slows down or speeds up that oscillation a little bit. And so now at the beam splitter, the second beam splitter, you have the two waves are no longer in perfect sync. So what used to be constructive interference in one port, the light would all go there. Now, if you slow down the wave by just the right amount, now you have the amplitude of the crest of one wave hitting the trough of the other wave, and you get destructive interference. So now all of a sudden the light no longer goes out through that port, it goes out through the other half of the beam splitter. And so if you have detectors at each of these outputs of the beam splitter, which detector will fire will depend on the phase shift. So it depends on how much you kind of impede it depends on how much you impede the sort of oscillation of the wave. And so this dependence of which output port you have on the phase, that's interference.
So interferometers are very precise ways to measure distances. So they're used, for example, to detect like gravity waves to just see, like, just because gravity is changing, like maybe the distances are changing a little bit. It can really measure, like, very small. If I change the path by like a fraction of a millimeter, it's enough to make like what before was like the crests meeting together, constructive interference. Now they're going down, so you can really detect this kind of. Right? So they're used everywhere in optics and in science, right? It's not something just in foundations.
And it's basically sort of a semi-transparent thing, right?
Yeah.
Exactly.
Each beam splitter is a semi-transparent sliver
So
of glass.
part of the laser bounces off and the part goes through.
Exactly.
Yeah.
And if you send a single photon through, then it takes a superposition of bouncing off and going through. And so you get this kind of coherent quantum superposition of taking the two paths at once.
Yeah.
Just like in a double slit, you have the coherent superposition of going through all possible paths to the detector.
Yeah. So we have a particle going through this beam splitter, this interferometer, and then at the end we perform a detection just as in the double slit experiment, and we either had a interference pattern or a pattern that shows that it was particle all along.
Right.
Yeah.
And now you can take this interferometer just like with the double slit, and instead of shining a laser through, you can shine a single photon through.
Yeah.
And that single photon behaves in exactly the same way. So it depends on the phase shift in one arm, which might sound a bit odd because if you think maybe the photon went through the other arm, then it wouldn't depend on this phase shift. But in fact, it always depends on the phase shift. So it's as if it always knows what's going on in both arms of the interferometer. You could even put a second phase shift in the other arm, and it depends on both of them. So even though it's a single particle, somehow it knows what's going on in both paths. And this is the sense in which it seems like it's a wave. It seems like it's traveling through both arms of the interferometer and picking up local information in one arm and also in the other arm. And so this is why we call it interference. And when you see this dependence of the output port on the phase, or the two phases, one in each arm, then we call this interference, and we think of it as this wave-like behavior. In contrast, though, if you put a detector in each arm, only one of those two detectors will ever fire. So it's like the particle's only going through one path when you check if it went through the path. So once again, it's like if you're checking the particle
double slit
properties,
again.
Yeah, exactly. If you're checking whether it's going through one or the other slit, it always is going through one like a particle would. But if you check, does it interfere and seem to have information about both slits, it always has information about both. It behaves like a wave. And so this is, again, that seeming observer dependence of reality.
Yeah.
And then Wheeler said, okay, let's take it up a notch. What if we imagine removing the final beam splitter before the particle reaches it, but after the particle has passed the first beam splitter? So now if this particle has to decide, do I go through one path because you're going to measure which path I went through, or do I go through both paths because you're going to ask me about the local phase informations? It has to have made that decision already once it passes the first beam splitter. It can't make that decision later, you would have thought. But what Wheeler showed is that actually, if you decide whether or not to put the beam splitter in at the end, you still get both types of behavior in the same way. So the particle still seems to be making this decision, is it a particle or is it a wave, despite the fact that you would have thought it needed to know that information all the way back at the first choice. Does it go through one or the other or both?
And has this been confirmed experimentally? These experiments
this has been confirmed experimentally, yes.
Yeah, so this one, when I read sort of what Wheeler said about it himself, you get sentences like the past has no existence except as recorded in the present. He spoke about, I think, even history creation, all a bit poetically, but it led him to sort of that participatory universe image, the famous view of the observer participating in the Big Bang coming about, and it's all just mesmerizing, cool stuff. But then I also read, of course, that there's much debate on how to really interpret the delayed choice experiment, right? There online you can find lots of videos like, whoa, you can't believe this, and like that, videos like, oh, quantum is really weird. And we have Sabine Hasselfelder, for instance, debunking it also in a very, very, in her own way. Anyways, and I don't know what to make sense. I don't know now what it really tells us. Do both of you? Or
Yeah, so this is something that I kind of study actively, and I spend a lot of time thinking about which of these phenomena that people say are weird and mysterious, like Wheeler was saying about this delayed choice experiment, are in fact, in some rigorous sense, weird and mysterious. So Bell came up with a kind of nice methodology where you kind of start with some assumptions and you prove a theorem that says any explanation within this broad class of explanations cannot reproduce the phenomena without having some bizarre properties outside the class of desired explanations. And so that's kind of what my research does as well. And so we look at each of these phenomena in turn: interference, delayed choice experiments, quantum erasers, teleportation, and so on. And we try to see whether there's an analogous no-go theorem, or if, in contrast, you can just construct an explicit model that can reproduce the phenomena without any of these bizarre features, like without any retrocausality, without any observer dependence, without any non-locality. Yeah. And in this particular case, for both interference and for the delayed choice eraser, you can actually make a simple model. It's actually quite intuitive, and I can explain it to you, where you have none of these bizarre features. It's just a particle that deterministically moves about along continuous trajectories, and nonetheless, it's able to reproduce these seemingly surprising phenomena. But as a consequence, then, if you agree with me that the model is simple, then you have to admit that actually this isn't evidence for any of those weird features that it was initially sort of imagined to be.
Whoa, there's a lot in here. First of all, I think good for people to understand sort of no-go theorems. So physicists then say, to account for certain phenomena, you say, okay, there are certain assumptions to be made, that have sort of ontological implications, for instance, locality or realism, whatever. And then Bell showed us that we can put that to test, that you cannot have both locality, realism as we commonly understand it, and, for instance, free choice. So one of those you have to let go, and that's a no-go theorem. You can put it to test. And you're now saying that there are these, you can apply this way of thinking on the delayed choice, and then it's not that weird. Is that what you're saying?
Exactly. If you try to come up with some similar argument as Bell did, you'll fail. You can't make a rigorous argument that it's weird. And quite the opposite. You can instead take the other approach and just start trying to construct an explanation. Mm-hmm. And actually, that's quite doable. We now have such simple explanations. And maybe it's worth me trying to give you such an explanation. You can,
but I really doubt if it will be that simple.
I think it will. I think you might be surprised.
Okay, check.
So let's start with just basic interference. How do we understand this weird kind of simultaneous wave and particle-like behavior? Well, think back to the reason that we thought it was a wave. The reason we thought it was a wave is because somehow the single particle seems to know that there's two slits there, and it seems to know whether the slits are opened or closed. It seems to know whether there's a phase shifter in one of the slits or one of the arms of the interferometer, as I mentioned. So how can a single particle, if it's really indivisible, traveling along definite trajectories, how can it know what's going on at two possible paths? It had to pick a path. Well, the answer is quite simple. It's the particle doesn't need to know what happened at the other path. Just something needs to know what happened at the other path. And the key here is that the vacuum in quantum theory is not nothing. The vacuum is something. So what's happening is as the particle goes through one path, it learns about the phase in that path, or it learns about whether there's a slit open in that path. Meanwhile, the vacuum, the zero particle state, goes through the other path, and it picks up local information about the phase. So the vacuum can carry information just like the particle. And so it's a bit like there's two particles, but one of them isn't a particle, it's the vacuum. And each of them goes through one of the paths, and then later they meet up again at the detector or at the second beam splitter, and they share that information with each other. Each one says, I know what the local phase was over here. The vacuum says, I know what the local phase was over there. And then using those local phases, after they both know the information, they decide which one will go to the detector and which one won't. And so it's local, it's simple. The particle is a definite particle. It's not a wave-like behavior at all. And the key is just realizing that the vacuum can carry information. And this is simultaneously a new idea and not a new idea.
Because it's totally new to me. I just find it funny how you talk about it, as if this particle can communicate with the vacuum. There's this information exchange, and that somehow can account for the quantum weirdness. It's just...
Maybe I can give another example of for us, if you have maybe a more naive notion of physics, you think, oh no, this is the particle, this is the thing I'm going to model. But more generally, we might be interested in like, let's look at the whole system. Let's look at everything that's happening here. How would I characterize what's happening there? Then maybe I put a vacuum. Maybe a more concrete example that lots of physicists who never think about foundations use in material science. When you think of like a current going through a material, so like there's many atoms there, and maybe there's like an electron going from pop, pop, pop. But sometimes it happens such that like so many electrons are moving that it's easier to think of a whole moving. So it's like the absence of the electron, because they're going in a direction.
Yeah.
You see like this whole moving to the other thing. And we treat this whole just like if it was an electron, but like with like with a relative positive charge as opposed to the electron, right? You can decide to model anything in your theory, and it just gives you a much easier explanation.
That's interesting.
Right?
Yeah, translating back to my trade of filmmaking, it's just a negative and a positive of an image in a sense, right? With the negative, I can get the positive. Yeah.
And in this case, like now we think explicitly about the particle is going through here, so vacuum goes through there.
It's surprising how large the set of phenomena you can actually find these simple classical models for. And often the explanation is one that's very analogous to the one I gave before. It's enough often just to think of the vacuum carrying information or something else of a similar nature, just kind of one missing assumption that with that on board, suddenly everything falls into place and you realize it's not so mysterious. So this includes things like teleportation, it includes steering.
So what classes also to you are like really that remain weird?
Yeah, so the phenomena that we don't know how to explain yet, I think there's roughly 4 of them. So there's Bell non-locality, which we've heard a lot about. There's contextuality. There's Wigner-Friend-like paradoxes and some modern extensions of it. And there's quantum computational speedups over classical computers. And those are really the sort of essence of quantum theory, the things that we just have no way how to explain.
And I know little of all of them, but the first one I heard you mention, and you also gave your talk about that, is contextuality. What is that?
So contextuality, it's kind of a generalization of Bell non-locality. It's essentially trying to formalize the similar questions to what Bell did. But the issue with Bell non-locality is you can really only ask, is a phenomena local or non-local if it's intrinsically some phenomena happening spread out over space-time and in some particular kind of causal structure. But if you have just a single system and you ask, does it have a local or non-local explanation? Well, of course it has a local one because it's a single system. There's no spread out entities in space-time. So what we wanted in our field was a kind of way to study non-classicality, basically how to make rigorous this idea of something being hard to explain for even a single system. You don't have to go to the context of the space-like separated experiment, just a single system, because so much of physics is done on a single system. And essentially, this is what we came up with as the best proposed notion of classical explainability. It's this notion of non-contextuality. So if you can find a classical explanation, then what we mean by that is that you're consistent with non-contextuality. And maybe I need to then define for you sort of philosophically what is the meaning of non-contextuality.
Exactly, yeah.
So non-contextuality is motivated by Leibniz's principle of the identity of indiscernibles, which says if you have 2 entities and there's nothing you can do in principle to see a distinction between those entities, so for every possible measurement you do, they behave in exactly the same way, then Leibniz's principle of identity of indiscernibles says those really must be the same object. Don't think of them as 2 separate objects. The reason they're indiscernible in principle is because they're really the same thing. And non-contextuality basically takes this idea seriously. And it says, when you take your quantum phenomena and you try to build a model of it, make sure that you respect that principle. And that's really one way of defining non-contextuality, is respecting Leibniz's principle. When you come up with this deeper ontological explanation for the quantum phenomena you're interested in, check whether every pair of indiscernible objects in quantum theory is described as the same object in the ontological model. And as it turns out, it's actually quite hard to make models that respect this principle. And if you can find a model that does respect that principle, we call it non-contextual. And that's a good classical explanation in our view.
The word that pops to mind that I know is invariant, so that it's invariant. It doesn't change Well, it doesn't depend on what context or how it is measured. It is what it is, and it will keep on being what it is, sort of, right?
Let me give you an analogy.
Yeah.
Okay. I want to make a theory of how to classify these animals. Okay. And here I have two animals. They both quack. They both walk in a funny way, right? So I would want a theory that tells me, oh, it's a duck. This is what's going on underneath, right? Because everything I cannot distinguish the two, right? So it's a duck. And a failure of non-contextuality is saying that, no, actually, we can show that even though everything we can observe is the same, any underlying model that explains this would have to give like two different explanations for this. Like it's a black duck and it's a white duck, but I cannot see color, right? So it has like this excess baggage, like excess ontology.
And you can show that with the mathematics
that
though it appears to be exactly the same, that in the underlying structure it is not. You can describe that mathematically or find that out.
Exactly.
That to me is pure magic. That how you do that.
It is magic, but it's magic that dates back to Bell. It's really following his methodology of we're going to start with some rigorous mathematical assumptions, and then we're going to derive some no-go theorem that says no such explanation can exist. And the hard part, of course, is how do you derive those arguments? But we've gotten pretty good at it over the years, inspired by kind of the example that Bell set.
And non-contextuality we should associate with classicality. That is what the world is what it is, independent of there's this underlying thing that's the same, and that therefore it shows us sort of the universe we have. And quantum is contextual.
That's right.
And what exactly then does that mean? I mean, what is then that underlying structure that gives a sort of different, or no, it appears to be the same, but is the underlying structure not the same?
Yeah, so if the world is contextual, then that means the fundamental ontology describing what's actually going on in a quantum world has these violations of Leibniz's principles. So there will be things in the world that appear to us to be totally identical. Even in principle, nothing you could do will ever tell them apart. And yet, fundamentally, ontologically, they're just doing totally different things. So it's a kind of conspiratorial description of nature where we're prevented from seeing the underlying mechanics that are going on. There's more detailed stuff, distinctions that are forever inaccessible. So it's in some sense, you could just think of it as it's like a worse kind of hidden variable. Hidden variables in themselves can have explanatory power, but you don't want that explanatory power to come at the price of some conspiracy where the way that they're generating the world that we see is sort of fundamentally misleading us. But these contextual models.
And what phenomena are we then referring to in quantum that are contextual?
Yeah, it's a great question, and one that we're kind of only really starting to study in its full variety in the last maybe decade or so. You can show that sort of some of the things I mentioned earlier, like Bell non-locality itself, implies contextuality. So that's evidence of weirdness in this sort. And that's not surprising, right? It just shows kind of consistency between these different notions that people agree are bizarre and difficult to explain. Also things like quantum computational speed up. So if you want a quantum computer that's faster than any classical computer, you're going to have some resource of contextuality that's powering it. So that is a proof of non-classicality if you can build a faster quantum computer. And then there's also more subtle phenomena. So I said that sort of a basic interferometer, that can be explained in one of these non-contextual, simple classical models. But if you take that interferometer and you sort of add some bells and whistles, maybe you change the reflectivity of the beam splitter so that instead of the particle splitting equal probability through both paths, you change that to be some kind of variable that you have control over, you can actually also get evidence of non-classicality with that extra bit of information. So it's kind of like the sort of basic phenomena, like interference in and of itself isn't weird, but some quantitative specifics about interference are still weird. And it's those quantitative specifics then that you need to use as a kind of resource of non-classicality, this weirdness that is both interesting but also useful for kind of information processing.
And we are now, of course, I don't know if I fully understand this, but what I do understand and find interesting is how it sort of relates back to, or we hit ontology here, right? Because you really are trying to understand what reality really is, its underlying structure. Just what are the viable options out there, you think, currently in quantum mechanics? I'm talking, of course, about interpretation of quantum mechanics, just the options we have ontologically that you find viable.
Viable or compelling? Because viable, I think we're all roughly in agreement that there's a number of viable interpretations. We have many worlds, we have cubism, we have Bohmian mechanics, collapse theories, some more recent approaches like relational quantum mechanics.
Yeah, Rovelli's take.
Rovelli's take.
Yeah.
They're viable in the sense that, they can explain our observations within a certain regime.
Yeah.
And they try to save one intuitive property at the cost of others.
Yeah, exactly. And do we have criteria to then distinguish between them? Is it just a way to come up with to agree how we can then find the best one? So then, of course, I'm also asking you, what criteria do you apply to say this one I find more compelling than the other one?
Yes, we definitely have criteria. The problem is we all have different criteria.
What are yours?
What are mine? My criteria, I think the biggest criteria, the one that really draws a hard line through a lot of quantum foundations camps, is, do you view the quantum state as something physical in the world? That's the psi-ontic view. Or do you view the quantum state as something that's just a description of our knowledge? And that's the psi-epistemic view. And I am solidly in the camp of the psi-epistemicists. So I think all the evidence points towards the quantum state is a description of our knowledge. It's not something that actually exists and moves about in the world. And so about half of the interpretations take one or the other approach. Roughly speaking, the sort of older, more popular in the past interpretations, like the big three, you have collapse theories, many worlds, and Bohmian mechanics. Those are all psi-ontic. But I think in recent years, the psi-epistemic perspective is becoming more popular, partly because we've been trying the psi-ontic approach for so long, and it's never really worked, and none of those interpretations have really gained a large following. But also, I think the sort of evidence that the wave function really is just knowledge, it wasn't really there until the last 15, 20 years, and we've really gathered all that evidence more recently. So that's why I think these approaches are taking off. And for me also, when I'm judging an interpretation, that's the first thing I check. I say, if it treats the wave function as something ontic, then I'm immediately very suspicious. I think they haven't basically updated the interpretation in light of all this modern evidence.
And for our audience to understand, saying the wave function is ontic is saying a particle is both at two places at the same time. If the superposition, if the wave function describes that it is at both at the same time, when I measure, I see it in one place, but it is really out there.
Yeah, I think that's roughly speaking right.
Yeah, and so that one you say, okay, if that's sort of at the core of your interpretation, it's not, I don't really take it seriously anymore.
That's right.
And you, Lídia, where are you in this? I'd say you're also a bit towards or pretty firmly in the epistemic approach, but
Yes, undecided, still on the fence, but yes, mostly yes. But maybe you can tell us a bit more about what is this evidence you see that the quantum wave is
that's
epistemic?
a good one. Yeah, because you said evidence, and I was like, okay, do we have evidence yet that epistemic ones are sort of...
Yeah, and in fact, this is something that I think there's some disagreement over. Like, does the evidence point one way or the other? Obviously, the reason many people are psi-ontic, take the psi-ontic approach is because they have some other evidence. But the evidence for the psi-epistemic view is more recent and I think just hasn't yet been widely appreciated. And so what is this evidence? Well, it's along the lines of what I was describing earlier, that you can take these specific phenomena, like interference, and you can ask, how hard is it to explain? Like I asked for these simple Leibnizian models, for example. When can you make me a model that's consistent with Leibniz's principle? It turns out it's so much easier if you take the psi-epistemic approach. For the vast majority of quantum phenomena, at the very basic level, like interference and teleportation, you can explain those phenomena, but only if you take the point of view that the quantum state is knowledge. If you believe that the quantum state is ontic and really physical, then it causes problems. All these explanations break, and you're back at stage one where all the quantum phenomena seem mysterious. So it's kind of like you look at the bulk of the phenomena and you ask, how far can I go in explaining these if I take one or the other approach? Currently, we can't explain all of them with either approach. So really, neither approach is yet sufficient, at least if you stick with the sort of basic background assumptions that we've tried to stick with for so long, then neither approach works in its entirety. But the one approach that goes much further than the other and can explain the vast majority of the phenomena is the epistemic approach. And it's precisely these Leibnizian models that can reproduce those phenomena.
And can you make it understandable or break it down? But I think this will be very complex to understand how exactly you end up with sort of this lumpy, messy explanations once you go psi-ontic, and where you keep it tidy and clean and just smooth with the the epistemic approach.
Yeah, and in fact, the original sort of epistemicist maybe was Einstein. So he made the first argument of this type. He said, let's look at measurements on an entangled system. So if you have some entanglement and maybe half of the entangled system is over here with one party and the other half is far away with someone else. And now if I do a measurement on half of it, what the quantum formalism predicts is that immediately the state you would use to describe the system over here will get changed as a consequence of your measurement over here. And that's sometimes called remote steering. And what Einstein said was, look, if the quantum state is really existing in reality, and you just told me it changed because of my measurement over here instantaneously, then I have some instantaneous action at a distance. And that was essentially the whole purpose of the EPR paper, was to point this out, that in order to explain that kind of phenomena, you needed to imagine that there were some underlying properties, that the quantum state itself wasn't the complete description of affairs. And so already just looking at this simple phenomena of measurements on an entangled system is problematic if you really view the wave function as existing in reality. But when you think of it as just information, well then when I do a measurement here, of course you're going to update your information about the state over here. So when the wave function changes, it's just a description of what this person knows about this system. And you remove the problem.
But it surprises me that you say that Einstein had this. I'd say he was just pointing to the implications of a psi-ontic approach and had trouble with that. But he didn't make that step, right? To go and say, I'm okay with that. It's just our knowledge of nature.
Well, I think he did. He was very interested in then finding some deeper description, so that the wave function would just be a sort of effective description of that deeper description. And if one could find such a description, he held out hope that eventually that description then would be a local account of what's going on here. And in fact, you can find local accounts if all you're doing is a single measurement on an entangled state. Bell's genius was to say, now consider measurements on both sides and change your measurements around, and then you can get sufficient evidence to show that Einstein's hope isn't going to work. You won't find some deeper
That
reality.
is not going to work. No, we need something else.
Yeah.
In general, the psi-ontic approaches, as you just mentioned, they were sort of the more earlier interpretations of the theory. So they've been given more sort of just explanation, attention, and sort of the popular media to play around with those concepts, etc. Whereas the epistemic ones are more new to us. I know, for instance, when one of them is cubism, and when I read that, I was like, what is he saying? You know, the stuff Chris Fuchs is just saying, and that it is a theory not of what nature is, but only what we can know about nature. And he's now talking about sort of an ontology of the measurement. So it's really putting, in some sense, the observer back at the center of the universe, though it cannot give us what the observer actually is. But he says it's just, he said to me, like, quantum theory is just a manual on how to make bets with the universe. And it doesn't tell you anything what casino you're in. It just gives you just very good ways to bet and update your beliefs and make better bets about nature. It's crazy stuff, right? But that is sort of the epistemic approach, putting the observer at the center again, and sort of it's a theory about what you can know and how to update your beliefs.
Yeah, so there's different kind of flavors of psi-epistemicism.
Yeah, this is cubism I'm sketching here. Yeah.
Exactly, and you've nicely described how cubism views the world, but I think it's one of the most extreme positions.
Okay, check.
And it's not the one that I subscribe to, and I think the majority of psi-epistemicists would say that really it is knowledge about some underlying reality. We're not just, it's not just a user's manual, but we don't yet know what that underlying ontology is. So, there's kind of different flavors of psi-epistemicism, and Chris was one of the first to take this epistemic perspective, but he's also now been the one to take it the furthest. And a lot of people get off the train before you go as far as the sort of radical subjectivism that Chris is pursuing.
Yeah. Because you say it's radical. Is it radical because it then seems as if it cannot give us an objective universe anymore, an objective reality?
Well,
sort of, yeah, he gets annoyed also when
Yes.
I ask him, when you say your theory is solipsist, right? He gets annoyed and then he has sort of an explanation for that. It is not solipsist, but I do get that people think it is.
Yeah, it's certainly not solipsist because it allows all the different agents to also be reasoning about the world in the same way and gives them sort of their own perspectives. But it's very pluralistic in that we're each in our own universe, essentially. And there's no sort of global picture that unites all those different into just the universe that we're all partaking in. Chris is looking for some underlying ontology and some underlying less subjective features. What can we say about the world? Not just making bets. But it's not something that's very well developed, I think, for the cubists as of yet. And it's also not something I understand very well, how they hope to get back to ontology from the sort of very subjective beginnings. But I think they're pursuing it, and they don't want to totally give up on the project yet. But
Yeah. And something else it cannot do very well yet, but again, look, Cubism is a relatively recent theory being developed by a relatively small number of people.
Yeah.
So,
Yeah,
I mean,
I know.
it's not a criticism of the end result, right? We're still in the process. But it cannot say much about like combining the experiences of different people, which we need to do physics and to do everything. Like I'm not doing all the measurements myself. I need to combine my information from information that you obtained. And you cannot say much about like these experiments, like these extended Wigner-Friend experiments, where we look at the perspectives from different agents. And, you know, it's okay if I say, look, no, it's just a tool to give me a good bet, right? But then it just hits a wall, and then there's some regime where we still would like it to make predictions, but then like Cubism doesn't have explanatory power there, right? It's just like, okay, it's not the right tool for this. Okay, but we're looking
But
for
what is then? And but is it right to sort of talking to both of you? What sort of dawns on me is that if physics was once an endeavor where a single physicist could sort of come up with a theory, do experiments, describe that accurately, and then hand it over to you, and then because we live in an observer-independent universe, you can perform those experiments, get exactly the same results. So that's all. So that's all the communication we needed in between us physicists, and then maybe you find a sort of flaw in my. But then you update the manual and give it to me. Now, with quantum and this epistemic approach, it seems that something else is at play that we have to. How does that communication work? Because if some of these experiments, I'm hearing people talk at this conference about it, seems as if I mean, for instance, Wigner's friend, you have to go to someone in a system and ask, what did you see? And then it could be something different from me. I'm talking here, I think, about sort of absoluteness of facts, something I've heard you guys say. Is there still an absoluteness of facts? It's so weird for me, but we are in a different era, right, of physics.
Yeah, I think this extended Wigner-Friend arguments you mentioned and the challenges that we now see, this is very recent stuff. In the last 5 or so years, there's these new no-go theorems that are kind of beyond Bell, which challenge not just locality, but as you say, the absoluteness of observed events themselves. And there is a sense in which I would say we're in a new era that the thing about Bell's no-go theorem was it's constraining these particular explanations that refer to sort of hidden variables and ontic states. And some people reject the idea that there's some underlying mechanistic description, these hidden variables. And if you reject those ideas, then you're not so interested in Bell necessarily. But what's new about these extended Wigner-Friend arguments is they don't at any point make an assumption about some underlying classical ontology described by these hidden variables. And if you're not making that assumption, then you don't any longer have this easy way out. If you're like a Copenhagenist or a cubist, you can't just say, oh, I looked at your no-go theorem and I noticed you used hidden variables, so therefore I'm not interested. now you have to go and you have to address these kind of more serious concerns, this new no-go theorem. And these theorems, in some sense, can be viewed as a challenge to absoluteness of observed events, as you mentioned, that when I do a measurement, I see an outcome, it's a single outcome, and it's definite. It's a fact that now exists in the world. It's not somehow specific to me, and I live in my own world because I observe this outcome. Absoluteness of observed events says the fact that I saw this outcome is an unqualified fact that exists for everyone. Even if others may not know what that fact is, it is at least a fact for them. But we thought this is a very natural thing. I think we all think
super common sense,
And yet there's challenges to it now.
Can you help unpack this,
maybe
Lídia?
The idea, I mean, the whole setup is a bit complicated, but at the end result, the idea is that you can have someone, whenever like David observes something, he can reason that I predicted with certainty that he would observe the opposite. Right? So there's a fact that is real for him, which is incompatible with my reasoning. And we're both applying the same theory to do these calculations. Right? So
the same theory gives different results, opposite results, depending on the observer.
Depending on like kind of the chain of observers you go through.
It's super weird.
It is, yeah. But I mean, again, now zoom out from the observers and think about what is a measurement. And then if you think about what a measurement is, then this whole idea of events being absolute, like outcomes being absolute facts looks very bizarre. Like, so what is a measurement? I'm trying to measure a photon, so I put a detector here. What's happening is that the photon is hitting some electrons, right? If it is a superposition of here and here, maybe there's a superposition of, if I just think of everything as a quantum system, right? There's a wave function that's propagating, or that's the explanation we have, right? And now I have a superposition of these electrons going this way or going this way, which will form some image in my detector. And then there's some photons coming from here to my eye. And this whole thing, you could zoom out and take like a quantum view of this whole thing. If you believe that quantum mechanics does not break down between like the atom scale and like the size of my brain. It's not that big, right? So, and if I'm looking at this from the outside, then everything that's happening is just a reversible, like a transformation, like as if I was like braiding some threads together. And it can in principle be undone. You can unbraid this. Like if you have sufficient power over like me, you can like undo this measurement, right? So it's very weird to think that I would assume that when I see something, this is an absolute fact of the universe that exists
it's
now,
so
right?
cool. It's so cool to hear that how you have this deep understanding of the theory that makes you that to you this already makes sense. It's nice. It's nice to hear you talk. I find it hard to follow, not because you don't explain it well, but just because it's so counterintuitive.
On the other hand, I mean,
to me, it's still that doesn't convince me. I'm still very concerned about the.
No. I mean, this is going to say, like, on the other hand, it's not useful for me to think of myself in being in this big superposition all the time, right? I have the subjective experience of just seeing one outcome, and I need to have a theory that tries to explain this one single outcome, right? So like I put like this artificial barrier between the quantum world and then my classical view at some point. So of course I want a theory that tries to make sense of this, but it's not so surprising to me that, well, then in this theory you cannot have facts being absolute events because they're not physically absolute events, no?
I don't share the same
view. You don't share the same view? Really?
Yeah, I don't. To me, it doesn't really matter if a future person could come and reverse the interaction. Like, I agree that a human observing some system doing a measurement is some big complicated interaction, which can all be described by just a bunch of quantum entanglement. But I think nonetheless, it's, to me, as just a...
I mean, it's what happens in these experiments, right? So in these experiments, in order to obtain these contradictions, you really need to have someone like go there and reverse the measurements.
Yeah. And does all of this sort of, how philosophical in a sense, though coming out of these no-go theorems, but how relevant is all of this? I mean, would it be that those discrepancies between observers, or how do I say it? It would it in the end be that this glass to you stood here, and my theory told me 100% it was here, and it's just this very small difference, but it doesn't really make any difference. The glass is still in a position that makes it, for all practical purposes, not a problem for us in real life, and not even a problem for us in physical theories. Is it like that, or is it something we really need to worry about?
I think for all practical purposes in everyday life, it's not going to have any effect. We're not going to sort of, and we kind of know this already, right?
Exactly.
If it did have consequences for everyday life, we would already be seeing them, and we would have realized these were problems long ago. But nonetheless, there are sort of concrete thought experiments that would involve a conscious being in the experiment, and the thought experiment is really probing sort of what they would witness. And so in some future, not at all everyday world scenario, but some very controlled specific experiment, we kind of begin to probe these weird phenomena. And so yeah, you can start to wonder, like, what would a person see if put into one of these experiments? And that is sort of what started the whole line of reasoning with Wigner.
I think it's too early to tell.
Yeah.
These experiments are all too new, and we have not just like generalized them enough, like explored enough of what they could be to say that, oh, we can't make a version that would be problematic in real life. We tried to come up with some ideas of like, oh, a computer is not a conscious being, but it needs to make some rational decisions according to some
it has
algorithm, right?
Form of
I need
cognition
to see,
that
if I see bit coming through here, I make the decision. If not, right? And a quantum computer, I'd want maybe the same thing. And some people are now trying to come up with scenarios where, maybe you have a little network of quantum computers and try to see if this kind of contradictions could also lead to errors and in some problems. And
it might lead to problems in quantum computing. This.
yeah.
And the consciousness in question.
Don't want to go there.
Don't make a short with that.
Don't get you started on quantum computing.
No, I mean, we don't know yet. Again, it's possible that we can come up with some scenarios where there's like one quantum computer measuring like a subsystem, like one processor, and we find some kind of contradictions, but we don't yet know how to make this into a problem. Right? Quantum computing has enough problems.
But what did you want to say, David, or in response to Lydia?
Actually, the consciousness in question in one of these experiments need not be a human. It could be something else. And in particular, it could be, for example, some artificial intelligence running on a quantum computer. I think if these experiments are to ever be done, that's sort of the most obvious first candidate for the kind of conscious being you could put in this experiment, because you need a lot of quantum control over that conscious being, and humans are very sloppy, messy, wet systems that are hard to control in sort of a coherent quantum way, whereas quantum computers are by construction very precise and clean. But if we could make a quantum computer that was running an artificial intelligence that was conscious, then you kind of have the best of both worlds. And so that's, I think, it's kind of the most promising proposal for such an experiment actually being done. Of course, it's far, far future technology, but
yeah. And then we're hitting, of course, on consciousness, which is very relevant for our audience. It's not your area of expertise, and it's a bit more into the realms of philosophy. But what are your ontological ideas there? I mean, most physicists, if I pin them down, say they don't know what it is, consciousness, or that it's not really relevant, or that it's just an epiphenomenon at the end of the chain in our universe, that we're sitting here, evolved animals with something we call consciousness. What is it to you, and what are your thoughts about consciousness as a physicist?
Yeah, that's a tough one. Largely, as you said, as a physicist, I wouldn't consider it my purview to make any sort of comments. But the slightly awkward feature of these extended Wigner-Friend arguments that refer specifically to observations and observers, they kind of are forcing me to start to think about these questions. And I've kind of, for a long time, didn't want to, because it feels inappropriate. Like previous attempts people have made to connect wave function collapse and consciousness, for example, have just seemed completely out of nowhere, just random Hail Marys, like consciousness is weird, collapse is weird, what if we put them together? That isn't a good argument. And as a consequence, I think people typically don't want to think of observers as somehow having any privileged role within quantum theory. Of course, there's some exceptions like Chris Fuchs, as we mentioned, but in large part, that's been the line that's been taken by physicists. But yeah, in recent years, I've started to wonder if that's too easy and if maybe we have to grapple somehow with these questions when we want to study these extended Wigner-Friend scenarios. But I'm not sure I yet know how we should begin grappling with them. It's just, I'm still beginning to be convinced that maybe somehow the notion of observerness and it's relevant to these particular experiments. And that scares me, frankly.
No, it
I don't
scares
know
you.
if you have a...
You've said that 2 times now. That just intrigues me. That you say it scares you. In what sense?
Well, if the problems of quantum theory are somehow require us to think about observers, then first of all, I'm very shocked. Like I'm very resistant to that idea because thus far there hasn't been any evidence that there's any real deep connection there. And secondly, it means that maybe progress will be very difficult and very slow because modeling an agent as a physicist is just unfathomably complicated. Whereas, the current level at which we model consciousness is like psychology. It's not even chemistry or biology. And to get all the way down to physics is an even more difficult task. So, I both kind of don't find it likely to be true. And also it would have challenging implications for the field if it were true. But I'm wondering if, nonetheless, I need to take it more seriously as a possibility. And I would love to hear an argument that sort of prevented that from being necessary, but...
we don't need
We don't
I feel my intuition, okay, is that we don't need a complex theory of consciousness for this. The only thing that we need is to connect somehow subjective experience of seeing an outcome or another outcome, right? The whole how I process this information once I have the subjective experience. I mean, this we can build a little quantum computer that just does a few logic gates that do this, right? And it's still a quantum system. This part is easy. It's just, I can have that, but I can't tell that this little quantum computer has a subjective experience of just seeing one outcome, right? Which is what we somehow feels that we need. And I'm not sure that finding a physical explanation for this subjective thing is necessary. I think it's maybe just one thing that is postulated. That I say, look, I postulate for myself because I see my own brain. That my experience is that I see one outcome. And I imagine that the same is true for everyone here. And then I can also say, I could do the same in principle for an electron. I just have no way of proving that the electron sees only one outcome, I don't know, after running such an experiment. So there's versions of this Wigner-Friend experiments where the observer is itself just one photon or one electron or not, right?
I think that's a very good point and a good clarification that I maybe made it sound a little bit like these experiments rely somehow on consciousness specifically, but really it's somehow more this subjective active observation and we don't need to assume very much at all about it except sort of that it's there. And sort of all the details of reasoning or being conscious, those aren't really needed.
That's so difficult. We don't have a consciousness test, and you're talking about phenomenological consciousness. That's the subjective experience of holding this glass. And the problem with conscious AI is that we'll very soon maybe get to the point that everything would seem as if they're conscious, but still they do not have that subjective experience, which we cannot test. The only thing we know ourselves to be true is that we experience the world in a defined state. So we know of our own consciousness that it only gives us reality in a defined state, right? That to me is something important to ponder upon, because I cannot observe something like a superposition. And then I am fully on board with you with this epistemic approach, saying, okay, then it's more likely to say it's a theory of my knowledge of nature, but I cannot say anything more about it. Yeah.
Yeah, although we also attribute consciousness to each other, right? I have my own subjective experience of consciousness, but I assume that you do as well. And is that merely because you're constituted similarly to me? Or so we can't just deny the quantum computer or classical computer its consciousness merely because it's a, mechanistic artificial intelligence, so-called. Yeah, so I mean, it's obviously going to quickly become a challenge to say, what is consciousness? Is this artificial intelligence really any different from us just because it's built differently? Yeah, I don't know. Obviously, these are hard
and maybe
questions.
to end our beautiful conversation, because I really enjoyed it, on a sort of more fun note, are there any sort of science fiction movies out there that sort of capture, not that I'm aware of, I really like Christopher Nolan's work. He did Interstellar, but that's more Einsteinian. It's sort of in a block universe. What is he? Is travel in the fifth dimension. But this real quantum weirdness, is there stuff out there you guys enjoy from sort of on Netflix? You think, this nails it? Or is it always sort of just, you think, this is like Hollywood's
I mean, okay,
BS?
let me give you one cool thing. Is that like the concept of quantum teleportation? Mm-hmm. It's like, okay, I need to get the timeline right, but I think it was invented after Star Trek. Like, as an inspiration, because, it's pretty much that. Of course, it's impossible because you need to make an amazing measurement in every atom of my body to teleport me, but it's like, it's this idea, right? It's more the other way around than...
fun. So it's up to us, filmmakers.
If I think of recent things, I don't know anything that's gotten it.
Yeah, there was an Apple show. What was it? Which was like heavily many worlds inspired.
Is it dark matter?
Yes. That's the one.
Okay, dark matter.
Yeah. So there's
And that captures sort of the many worlds.
in a very liberal way. Yeah.
Yeah. And on a more, and all our conversations in this conversation, I'd like to bring it back also to our audience. It does. I also had sort of this talk with Chris, sort of on a more personal level, that, and of course, that goes back to sort of your human intuitions about the work you do as a physicist. Who am I in all of this? That he said stuff that he just likes the universe, to think of the universe as sort of a place where there's something like true novelty or true creativity in our universe, which a many worlds theory, he said like a many worlds interpretation gives you sort of, in a sense, that universe that, you know
a
what I
world
mean?
where everything can happen is a world where nothing happens. It's like
Exactly. So, and then from a human, and that's not what a scientist should do, but just a human intuition is, okay, I like that more. And I'm curious how your work and thinking about all of this, has it changed your outlook on life, and does it affect the way you just look at life and relate to people? And
I think I'm kind of mostly just left with kind of a recognition of how far we have to go, that like I'm looking for the simplicity, and we don't have any of the answers. All the answers we have are very uncompelling to me. And I think, these are the parts of nature that we have the most control over, the most knowledge about, and we still have so much uncertainty about what's going on. And so then I just think how much harder it is, if you're a psychologist or something else. And it's kind of amazing to me, like how much progress we make despite the difficulties. We have the most precision and the most information. We can predict some quantity to 10 decimal places, and we still don't know what the theory we're using is actually telling us about the world. And then we're supposed to navigate a human world, and it's just baffling that we succeed as well as we do.
oh, that's so funny, and it's also a bit sort of tragic in a way. But also the amount of time you guys put into this, and then of course for all the bells and the people who get awarded and stuff, there are of course thousands of physicists who just put in all the hard work and don't always get that recognition. So it has to be that you're really driven every day in sort of your pursuit of knowledge and truth, right? That keeps you going, I guess, right? So yeah, that's nice to hear. And I could see that fire in both of you. Thanks so much for this wonderful conversation. Thanks, David. You really got me thinking. Really need to listen back to this talk, to everything said, and help our audience understand it. And to me, it's just very cool to see. It's exciting, I think, the foundations of physics at this time. It's an exciting branch to be active in. I hope.
More than ever. Yeah. And thanks for having me.
Yeah, thanks so much. Thanks, Lídia, again for helping us understand things better, adding questions. Thanks so much. Thank you for watching this conversation. If you like the content we put out, please subscribe and like it, and comment if you have questions to David or Lídia so we can follow up on those. And see you in our next talk on quantum mechanics, consciousness, and metaphysics. Thanks for watching.